Last video for this section. We're almost there. So I've written a theorem up here, which just puts into mathy words what we just saw. But it also points out an interesting concept that we have. So we're trying to find regions, areas of regions in the xy plane. And we have to think a little bit about something that we mentioned last time when we were finding areas of regions in the plane, where sometimes it's easier to represent our region using the idea of top curve minus bottom curve, right? Functions in terms of y in terms of x are easier to define that region. Whereas sometimes if we see it was easier to represent something like left curve minus right curve, like this next example that we're going to do in a second. In that case, right curve minus left curve is really doing x is functions of y. So a right curve is really x in terms of y minus something x in terms of y. So we've got two different options. So if it's easier to define the region using functions of x, so to see where does y go from into in terms of functions, and then use x as numeric bounds, then we'll do like we just did. Right, we'll put our function bounds on the inside, integrate with respect to y, and then do that in terms of our function, or our, scalar bounds of x, those numeric bounds of x. If we do it the other way, if we decide to do it as like a right curve minus left curve, well then really my function bounds are, we're saying that x goes from between those functions of y, so like x goes from h1 to h2. So that needs to be my inside integral. We need to integrate that first. So notice we're going to do the dx part first, and then do that in terms of y, where y goes from some constant to some constant. So we do have the ability to change the order of integration, but we have to do it strategically, and it means something different if we change the order. So we can't just willy-nilly flip the order of integration because it means a very different thing, but we can in a situation choose which order seems to be more effective or more simple, I suppose, for the example that we're trying to do. So for instance, let's try and do an example. So we want to find the region bounded by y equals x minus 1 and y squared is 2x plus 6. We would have to graph those probably to see what this region looks like. So you can try and do that, but I've gone ahead and sketched part of the graph. I didn't put all of the key information because if we think about back to Calc 2 when we were doing all this, if we think about what this region is defined by, part of what we need to take a look at is, well, where are these intersection points? We have a little bit of an idea that we're probably going to take a look at this region as being right curve minus left curve. Because notice, the right curve is entirely the sideways parabola, whereas the left curve is the sideways parabola, the right curve is the line, right? So x is going to go from the lower bound of the parabola to the upper bound of the line, but then we have to figure out where do those y's cut off, right? Where is this and where is this on the y-axis? So we need to find those intersection points. So we can come over here. It already might help to take a look at the idea of, well, if we're doing right minus left, then really I need to figure out, well, what is x in terms of y? So what we're most likely going to do is restructure these to put them in terms of an x equals equation, because then we can see what x goes from. Pretty easy with both of them, right? We just need to move some stuff around. So just add the 1 over. So x is really y plus 1 there. And then here we need to subtract the 6 over. So we would have x is going to be y squared minus 6, and then we'd have to divide that 2, so everything divided by 2. If we want to rewrite that one, we could instead write that as y squared over 2 minus 3, since 6 over 2 is a nice number. So part of defining this region, we can already see that x goes from that parabola portion, which was this guy. So it goes from y squared over 2 minus 3 to the line portion, which in terms of x is y plus 1. So what we really just found is our bounds for our x variable. Now what we still need is my bounds for y. So in order to find those bounds for y, well, we need to find those intersection points. So we've got our x equals and x equals, so let's find where they intersect. So we'll just set them equals to each other, right? X equals x, so we'll have y plus 1 equals y squared over 2 minus 3. Get everything on one side, so we'll have y squared over 2 minus y. Subtract another one, so we'll have minus 4. All equals 0. It might help out if we're taking a look at that to just clear out that denominator. So if we multiply everything by 2, we'll get y squared minus 2y minus 8 equals 0 times 2 is still 2, or sorry, 0 times 2 is still 0. Math hasn't changed that much since we went online. And then we just need to factor this. So factoring this guy, we just get x. We'll need a minus 4 and a plus 2. Oops, except for y's, not x's. This is why I need you all here to catch my mistakes. To catch them all now. Roughly. So we're going to have y is 4 and y is negative 2, which does kind of make sense based on our graph, right? Down here we go from negative 2 up to 4 on the y-axis. So notice we're looking at the x-axis is function to function, so parabola to line, and then on the y-axis it's what bounds are we looking at that from, so what numeric values are we going from, and it goes from y equals 2 up to y equals 4. So what we would need to do at this point then is come up with our integral that we're going to do. So now we're going to have our area. I'll squeeze it in here and then I'll let you guys try and work on the integral and I'll jump back on in a second. I guess I said this was our last video. You can watch me erase while you work on it. Our area, we have to think about which order to do it in. Now we have to think about our order of integration. Remember, my inside integral needs to be the function bound. So in this case, my function bounds are with respect to x. So this is going to be a dx and then a dy integral. So we're going to have an integral of dx dy. Now remember, in this case, we just integrate with respect, or we just integrate an integrand of 1 so that we get a two-dimensional area. X, we said, goes from the y squared over 2 minus 3 up to y plus 1. And then y, the outside bounds, goes from 2 to 4. So notice on the bottom, or on this bottom bound on the inside integrand, we are going right lower curve to higher curve, which for x's means left to right, right? For x's, left is smaller, right is bigger. So we go smaller, bigger, meaning left, right for those. So that's my bottom curve is smaller, my top curve is bigger. So I'm going to pause the video for a second and erase the other board. Why don't you start working on this integrand, try and practice it, and when you're ready, replay the video and we'll jump back into the solution together. All right, hopefully you caught my mistake already, right? I just didn't put a negative. This is why I need you all here. Right, y goes from negative 2 to 4, and so all these are negative 2's. If you missed it, just click change it in right now. So as we're working on this, we're going to do dx first. So integrating 1 just turns into x. So we're going to have x goes from our function bound, so y squared over 2 minus 3 up to y plus 1. So we've got a little more complicated function bounds this time, but still perfectly reasonable and we know what to do with them. Once we plug those in, that's still inside the integral from negative 2 to 4, where that's going to be dy. So top curve first, we're going to have y plus 1, and then we're going to subtract, plugging in the bottom curve. And notice we're just plugging them into x, so it just is the function itself. So we'll have minus y squared over 2, and then minus the negative 3 gives me a plus 3. And that's going to go from negative 2 to 4 dy. So integrate y goes to y squared over 2. Integrate 1 goes to y, because we're doing dy's, remember. Y squared will go up to a y cubed, and then we divide by that 3, so now it's over 6. And then we'll have plus 3y. Yes, I could have combined the 1 and the 3 beforehand to help out, but oh well, we got to where we needed. And then we just need to plug in those bounds. So as we're taking a look at this, we're going to have, right, plugging in 4, we'll get 4 squared all over 2. We'll have plus, I'll combine them now. We've got y and 3y is 4y, so we've got 4 times 4. And then minus 4 cubed over 6. And then we're going to take all of that and we're going to subtract, plugging in negative 2, so you're going to have negative 2 squared over 2 plus 4 times negative 2, and then minus negative 2 cubed over 6. And I'm not going to go through the arithmetic here with you, but if you do simplify it now, assuming that we haven't made any errors, let me just take a peek over here. We should then end up with 62 over 3. All right. Hopefully this is making some sense. If you need any help, definitely shoot me an email. We can set up some time face-to-face. What we're going to talk about in our next set of videos, which if you want, definitely take a break in between this set and the next set, kind of do some practice with these. This would have been, in essence, Monday's material if we were all together in class. What we're going to take a look at is, well, what did it mean when we had these double integrals, the integrand, the thing we're integrating, wasn't just a 1, it was a function of x and y. So when it's a 1 here, it represents an area of the xy plane. What does it represent graphically when that's a more complicated function? So that's what we're going to talk about in section 4.2. It'll be a blast. Like I said, let me know if you have questions or need any assistance with things. But I'll see you in the next set of videos.